Hello, and welcome to more nonlinear functions and their graphs. And really, this is all about polynomials. So let's take a look at a definition. A polynomial function of degree n in the variable x can be represented as such. So f of x is equal to a sub n x to the n power plus a sub n minus 1 x to the n minus 1. This numbering is just coefficients and then x to some power n minus 1 we count down, so n will be the highest. First power we never write, x to the 0 is 1. So we have all these constants that are a subscripts, and we have these powers of x, and we write them in decreasing order. Okay, so each coefficient ak is a real number. A sub n cannot be 0, so this leading one cannot be 0. And n itself has to be a non-negative integer. So our counting numbers are non-negative integers, right? Okay, our natural numbers. The leading coefficient is a sub n. The degree is n, it's the highest power. The leading term, it's not typed here, but the leading term is a sub n times x to the n. And the constant is down here, the one that doesn't have the variable with it. Now, the domain of every polynomial function is a set of all real numbers. And its graph is continuous, it's smooth, it doesn't have any holes or pointy spots. Pointy spots like, that's the non-technical term, that's my term for it. Cusp or corners or things like that, like the V-shaped absolute value graph. A polynomial will never have that sharp cusp or that corner like an absolute value graph. Okay, but polynomials do have some other things that we need to consider. And so let's think about any value of c in the domain of f. A specific value of c, it's not any value of c. We say that f of c, the y value, is an absolute or global maximum if f of c is bigger than or equal to f of x for all x ever. Ever. Okay, so in this graph down below, there is no global maximum because there's no value that is bigger than all others. This graph continues forever going up, so there's no absolute maximum. I'm going to write that here. All right, f of c is an absolute or global minimum if f of c is the smallest compared to all other f of x's in the entire domain. So what's the lowest value? That's right here. And so whatever this point might be, it looks like maybe it is 2.3 comma negative 19. 5, 10, 15, 20. So if that's not that, it is 13. Oh my goodness, it's probably negative 14. And I can't focus in right now. Here we go. Each little line is worth 5, 10, 15, 20, right? So we have 5, 10, almost to negative 15. I'm going to call that negative 14. This is the absolute minimum. Where is the 2.3? What is the absolute minimum? Is the negative 14. That's the lowest it goes. All right. F of c is a local or relative maximum if f of c is bigger than f of x for all x just near c. So here we have a relative maximum because near there, in this little area around all these x values, that's the tallest y value. We see we have another relative maximum at about 1/2 comma 1/2. In this little area, that's the largest that this graph gets. And f of c is a local or relative minimum if f of c is lower than all of the other x values. So here we see that we have a relative minimum. Here we also have a relative minimum because anywhere near this x value, that's the lowest it goes. All right, relative minimum. And this is also a relative minimum. An absolute minimum or an absolute maximum, there will be one highest number. There will be one lowest value that this function hits. Only one. But relative mins and maximums, that's going to describe all of our turning points. Notice this is only when the graph goes from, say, increasing to decreasing. Oh, now it switches again. So we're going to see a lot of that here in college algebra and pre-calculus, and definitely some foreshadowing for what goes on in calculus. Okay, so let's do it again. Let's find the local and absolute extrema for each graph. First, I'm going to find the local extrema. Okay, this graph continues forever down. So locally, I have a local max. I'll use a capital M. I have a local max. I'll use the capital M again. That's not going to work out for me, I'm sure. And here I have a local minimum. All right, little m. There's only one local minimum, two local maximums. It happens that this is also the absolute maximum. Global maximum is the same place as a local maximum, and it's the highest the graph ever gets to. But since the graph continues down forever, we will not have that same. Sorry, putting that absolute in green. All right, so absolute maximum, absolute minimum. This graph goes forever up. This graph goes forever down. There is no absolute max or min. The graph continues forever up and down, which tells me that this will be a local maximum, and I will have a local minimum. Remember, if we're reporting the values themselves, we would say the local maximum, let me see, I'll put it over here. Local maximum of 1.5. Local maximum of 1.5 at negative 2.1. Okay, so what is the maximum? 1.5. Where is it? Negative 2.1. The y value is what it is, and the x value is where you can find it. And it depends on how the question is phrased as to how you would answer these particular problems. All right, so how might we use these in reality, in our real world? In colder climates, the cost of natural gas to heat homes can vary from 1 month to the next. The polynomial function given by this f of x here, f of x equals negative 0.05. Let me see, turn on my calculator. Negative 0.1213 x to the fourth plus 3.462 x cubed minus 29.22 x squared plus 64.68 x plus 97.69. Wow, that's an equation. I have it typed into my calculator already, or else I'd be wasting minutes as I typed it in. I have my function. Okay, great. This models the monthly cost in dollars of heating a typical home. The input x represents the month, where x equals 1 corresponds to January and x equals 12 corresponds to December. Where might the absolute extrema occur for 1 less than or equal to x less than or equal to 12? Well, it seems to me, let's just think about this, the cost of heating a typical home. All right, so we're heating a typical home, and I guess this is very North American centric. CA, there we go, North America centric, as I find that many textbooks are. When I'm heating a home, it seems like the highest cost, so an absolute max, maybe in December or January. But the absolute lowest we have to pay to heat our house is probably maybe July. I'm here in the United States, so yeah, definitely. We're paying more in the Southwest to cool our houses in July, but there's absolutely no cost to warm it for me and my family. Why is that? And that's just because North America weather patterns. That's just how it is when we live here. So I have my function f typed in already, and I've adjusted my window. These scales say x minimum, x maximum, x scale. And then, so by y values, y minimum, y maximum, y scale. I have those values substituted over here. When we graph, we end up with this really, it almost looks like a cosine curve. It's pretty cool. So now we want to find the absolute extrema. It looks like it's over here is where the graph tops out for the first time. So we're going to calculate, that's in blue, so I'm going to push second and then trace. I want to find a maximum. And the maximum is, it'll find absolute or relative. It's just going to find the maximum. It's going to find the relative maximum. It's up to the user to know if that's absolute or not. So where's the smallest? Where's the left bound? My calculator's asking for a left bound, so I can scroll, or I could just type in a value that I know is to the left of that high point. I'm pretty sure it's right there. Now I'm asking for a right bound, being asked for a right bound, so I'll bring it over here. Fantastic thing is you don't have to be clever with your guess. I'm just going to press enter. And I find an absolute maximum. Hold on, gotta let my dogs out. All right, dogs are out. I'm not really into editing, so I'll just pick up where I think I was. I'm trying to write here, absolute maximum is at the point 1.4595644, comma 140.06051. So what this tells me is about midway through January is the absolute maximum heating cost of $140.06 for that month. But it also tells me, if I go back to my calculator over here, I can calculate again. So blue button and then calculate. I could calculate a minimum. And it looks like our minimum is here. So let's scroll over, get my little spider cursor a little bit closer. A left bound. Pick an x value that you know is to the left of that minimum, a right bound. You'll want to choose an x value that you know is to the right of that minimum. And you can move for your guess, or you can just let the calculator guess by pressing enter. My absolute minimum occurs at 7.1219697, comma 14.778211. So I would say first week of July is the absolute minimum heating cost of $14.78. I'm going to round that up. 778 is going to round up to 14.78. So we could use this to analyze electric bills in various locations. That's probably pretty close to maybe, I'd say a little above, probably some Utah climates. That might be a accurate. Okay, total guess. Now we have some more definitions. A function f is an even function if f of negative x equals f of x for every x in its domain. So input a negative value is the same as inputting a positive value. The graph of an even function is symmetric with respect to the y-axis. A function f is an odd function if by inputting a negative x, it results in a negative output, so a negative y value, for every x in its domain. The graph of an odd function is symmetric with respect to the origin. All right, so let's look at these even functions. For an even function, f of negative x is equal to f of x. So if I put in a negative 1, I get the same output as if I put in a positive 1. If I put in a negative 2, I'll get the same output as if I put in a positive 2. And that's why we say that's how the f of negative x compared to f of x works. But the symmetry, if you draw a line right down the middle, right down here on the y-axis, and then I fold one side over the other, it's a mirror image. So when I fold it on the y-axis, do I have a mirror image? Why, yes, I do. Mirror image on left and right. But we can also see that if we put in 3, or if we put in 1, 2, negative 3, we end up with the same height on the graph. Whereas with an odd function, inputting a negative x value gives you a negative y. So here I have the point 1, 1. If I change my input to a negative 1, my output also changes to a negative 1. Let's try this again. Well, there's no other good points in there. All right, but change the input sign to a negative, it changes the output sign to a negative. It's almost like we're kind of cutting the graph right here and then rotating it around, and we have a mirror copy there. So it's kind of like, I'm going to say almost like, so it's like a double, I swear if you tell people I said this, I'll deny it. It's almost like a 180-degree rotation. It's not. It's symmetric with respect to the origin, but it's very similar to this idea. Here we can see some examples. If I have the point 2, 0, when I put in a negative 2, oh, it doesn't change the sign of the y value because 0 doesn't have signs. So anything that's on the axis, it's really hard to tell, is it even or is it odd? But any point, say here, if I input 1, my output is 1, 2, yeah, we'll call that 3. And what do I have down here? Down here I have the point -1, -3. Oh my goodness, these examples are always all the same. I just realized why I don't like to teach this through example. But I'm going to show you how to do it algebraically. Because after a while, it could get a little confusing on what do you mean input, output, how does this switch, how does that switch? So let's look at the definitions. So I'm going to test this function to see if it is odd. And to be odd, if we change the input to a negative, our output should turn negative. All right, so that's what we're going to check. So first of all, I know that f of x itself is x cubed minus 2x. F of negative x will be negative x to the third power minus 2 times negative x. And now we simplify. A negative to the third power is negative. X to the third power. Negative 2 times a negative x becomes a positive 2x. So I know exactly what f of negative x is. What is negative f of x? Negative f of x multiplies our function through by a negative x cubed plus 2x. We'll look at that. These two values are equal. Since f of negative x equals f of x, this function is odd. Now, if it's a function, it cannot be both odd and even. It can't be odd and neither. It can't be even and neither. So once you find its symmetry, you're finished. So this one happens to be odd. All right, let's try that again. So I'm going to try odd. I'm going to find f of negative x, which is negative x squared minus a negative x cubed. Negative x times negative x is a positive x squared minus a negative x cubed. Negative cubed is negative, so subtracting a negative makes positive. I'll get positive x cubed. All right, so if this function is odd, then f of negative x should equal negative f of x I don't want to write that there. I instead want to write this down here. And I see that the f of negative x doesn't have a negative in front of the x squared, but my negative f of x does. So this is not odd. All right, so let's see if it's even. Remember, if a function is even, then f of negative x will equal the same as just f of x. So let's find f of negative x. So that's negative x squared minus negative x cubed. All right, we just did that. We know that this simplifies to x squared plus x cubed. And I see that x squared plus x cubed is not equal to f of x, so this is not even. Since this function is not even nor odd, this is neither even nor odd. And that's it. We have to test for both in order to determine if it's neither. Last step, I always start with odd. And actually, we don't even need to do that. As I was talking about this, it actually occurred to me that this process is really just straightforward. What I need to do is I need to find out what happens to f of negative x. If it comes out as negative f of x, it's odd. If it comes out of regular f of x, it's even. Otherwise, it's neither. Right? I don't have to set up these steps each time. I just need to find f of negative x once. Negative x all squared plus 7. Negative x times negative x is x squared plus 7. And then I compare. I know that negative f of x is negative x squared minus 7. So no, it's not odd. I can see that my f of x, x squared plus 7, is exactly what I get. It's exactly equal to f of x. So this function is even. My favorite thing to tell students, and really some of your favorite things to hear, are cheaters' rules. I'm going to scroll back up very slowly. I'm not going to make anybody sick here. Notice how everything in this polynomial, f of x equals x cubed minus 2x, all of the exponents on x were odd, 3 and 1. The function was odd. So I'm going to say all odd exponents, your function will be odd. And this is only for polynomials. All even exponents or constants, and that function will be even. But if an odd function has a constant, the overall result is neither. And if it's mixed, we will end up with neither. So it's a little quick and dirty check, cheaters' rules, to determine whether a function is even, odd, or neither. Or last example, and we'll wind up this extremely long video. This table is a complete representation of f. Decide if f is even, odd, or neither. Okay, so if I input 1, I output negative 5. So an x value of 1 goes to a y value of negative 5. If that's odd, negative 1 would go to positive 5. So I check. Oh yeah, that works. Possibly this is odd. I know that 1 and negative 1 do not give the same result, so this is not possibly even. Let me let me use the tens. Since f of 10 is 23, but f of negative 10 is negative 23, this is not even. And that's because f of 10 is not equal to f of negative 10. So if it's not even, I check all of them. 10, 23, I change the 10 to a negative, my output becomes negative. 100 goes to negative 56. If I change my input to a negative, my output changes sign and becomes a positive. Every time. Every time, if we change the sign of the input, we end up changing the sign of the output. Doesn't matter if the input started positive or started negative, we change the sign of the output. This is an odd function. So either we get the exact same thing back, or it changes signs when we change the input, or it's just helter-skelter. All right, that's it. No chaos in our math. This was an odd function. Thanks for listening.